So today we have Costis in our seminar for his very recent work on the complexity of min-max optimization. So Costis, I will let you take it away now. And any questions in the chat, please, and we'll manage them.
All right. Thank you very much for the invitation, and thanks to everybody for being here. It's a great pleasure to talk at UDM and the Vibrant group in Montreal. I admit I would really like to be in Montreal and you know enjoy the Montreal life, but we'll postpone that to some other better time. So I'm going to talk about the complexity of min-max optimization. And before I do so, let me start with a thesis, maybe an obvious one for some, maybe a controversial one for others. But you know, so my thesis is the following: that minimization is to current AI what min-max optimization is to future AI, or more broadly, what multi-agent equilibrium learning is to future AI. So minimization is a situation where an AI agent is learning and making decisions in a stationary environment. But of course, many environments do not have that nature. Thus, one has to go beyond minimization and consider min-max optimization and equilibrium learning, which is learning and decision-making in a changing environment, which could be changing because there is another one, or multiple other learning agents that are learning and decision-making at the same time, and which may have conflicting or aligned interests, but in any event, influence the experience of the AI in question, the one that's trying to optimize. Or it could be because noise or adversaries that are either currently present or are anticipated in the future may be poisoning or corrupting the data that our AI agent is currently experiencing or might be experiencing in the future. Or a min-max optimization or equilibrium learning problem may arise because indirectly, because we want to enforce constraints on the learning outcome. And this is, for example, the experience we have with training GANs, other adversarial learning training applications, and other types of applications where indirectly we need to introduce other agents to enforce constraints on our learning agent. So with that sort of like small intro about min-max optimization and its role, and equilibrium learning and its role in the future of AI as I see it, the focus of today's talk is about this very specific problem, min-max of some function f of x and y, where x and y are high-dimensional and potentially constrained variables. So of course, this problem is classical. It has found a lot of applications, mathematics, optimization, game theory, and a lot of other fields. So the best case scenario for this problem is when f is continuous, it's convex in x for every y, and concave in y for every x. In that case, the classical result by von Neumann says that if the constraint sets are convex and compact, then this problem, min-max of this function, is equal to the max-min version of the problem. And the interpretation of this equality is that if x star is an optimum for the left-hand side and y star is an optimum for the right-hand side, then this pair, x star, y star, is an equilibrium of the zero-sum game where the min player pays the max player an f, x, y dollars for a choice of actions x and y. So as observed by von Neumann and then Danzig as he was developing linear programming, and Adler, who was a student of Danzig and sort of like completed the picture very recently, equilibrium computation and convex programming are actually equivalent computational problems. Moreover, min-max optimization is intimately related to the developments in learning theory. And in particular, it's known that if the min and the max player run no-regret learning procedures, then their joint behavior in this average sense shown here So the average of the trajectories that the two players are gonna, are gonna be computing as they're interacting is gonna, at least in value, converge to the value of the equilibrium. In any event, these are all classical known facts. Zooming to the present. So min-max optimization has found a lot of interesting applications in machine learning. So generative adversarial networks and training against adversarial attacks are some of these. And these modern applications have exacerbated the importance of first-order methods, because typically these problems are very high-dimensional. Last iterate convergence to avoid the known oscillation behavior of gradient descent in these types of problems, and looking at non-convex, non-concave objectives, which is the focus of this presentation. So I'm gonna jump right in. So I was gonna say, describe, kind of like summarize some of the recent results on the frontier of coming up with learning procedures that converge not in the average sense as these classical procedures from online learning theory, but in the last iterate sense. So there has been a lot of beautiful work recently, including by many people in the audience, on coming up with procedures that converge to equilibrium in the convex-concave setting in the last iterate sense. But I'm going to skip those results because I want to shorten slightly my time, okay? So I want to focus on the problem on the very challenging front of non-convex, non-concave min-max optimization. And over there, the first thing I want to address is what is even the goal in that case? Because when the function fxy is not convex concave, then von Neumann's theorem breaks. And in particular, for some function f, the min-max is not equal to the max-min. For other functions, equality holds, but there are multiple and disconnected solutions. So in the convex-concave case, one of the nice features of von Neumann's understanding, and that coming from convex programming, is that equilibria are convex sets, and if the function is strictly convex concave, they are unique. But if the function isn't convex concave, then both the equality breaks, and also there may be, even if it holds, there might be multiple and disconnected solutions. And two very easy examples showing that are shown here in the picture. So this function here is not, it is concave in y, so that's good, but it's not convex in x. And as a result, you get two saddles. Over here, you have a function that is convex in x but not concave in y. And in this case, the min-max is not equal to the max-min. So in view of this von Neumann's theorem breaking, the question is, what is the goal when we're facing a min-max optimization problem like that? Which is what I want to discuss a little bit now. So the problem for my talk, the problem I want to be considering is that you have a continuous function f and a convex and compact set S, and your goal is to minimize over x, maximize over y this function, and you have a constraint on both of the variables. So that's a slightly more general version of the problem that I want to be considering. So again, if the function isn't convex concave, what is even the goal? And what I want to describe are three solution concepts that have been considered in the literature, but there are multiple other ones. And to describe them, I need a little bit of notation, so please bear with me. So I want to define these sets. So fx dot are all the y's that are consistent with x. S subscript x are all the x's for which there is some y that is feasible. And I similarly define s dot y and s subscript y. Okay. So now, with this notation in place, the obvious solution concept that is not a global mean, global max solution is to be local in the min player and global in the inside player. Okay. So one thing to note that I didn't explicitly noted is that if f is continuous and these two sets, the constraint is convex and compact, this problem is well defined. So in principle, I could be targeting that problem, but it's impossible to solve problem when the function is not convex concave. So the first compromise I may try to consider is to be locally minimum with respect to x and globally maximum with respect to y. So in particular, I might be looking for feasible points such that for some little neighborhood delta, I satisfy this constraint. So let me parse it for you. I want that the y player has no improvement. So the y player, no matter what he chooses that is compatible with x, cannot increase the objective function. For the x player, which is the outer player in this optimization problem, I want that there is no local move for the x player, so that in anticipation of the best response of the y player, there is no improvement for the outer player. So this is sort of like this take here is a sequential view of what this game here represents. It's the view that the min player moves first and then the second player moves. So the outer player should strategize in anticipation what the inner player is going to be doing, right? So, and this is what this inequality here is trying to say. It's saying that for every local move, so for every move of x in the neighborhood of x star, so x is considering only local moves, and in anticipation of the best response of the inner player, the function should not be decreasing. Okay, so then taking a sequential view of this game, what this says is that no player can improve. And in particular, the inner player is considering global moves and they cannot improve. The outer player, and that's the first compromise that I made, is considering only local moves. So the outer player is only looking at his neighborhood, and he doesn't want to see an improvement in anticipation of the best response of the y player, which again is going to be doing global moves. So that's take number one. So that's the first compromise where I went to this problem, which is otherwise well-defined. And instead of asking for both players to be globally optimal, I asked the outer player to only be locally optimal. The next compromise that I can do is I can make both, and that was proposed by Jean et al., is to make both players local. Okay, so, and I'm not going to write down the definition to avoid, the notation, but a local minimax solution as proposed by Jean et al. Is that both the outer player and the inner player are only considering local moves. But otherwise, it is the same sequential view of what this problem represents. The other take that I want to discuss is a take that we took in a paper and also Mazurman a couple of years ago, considered a couple of years ago, is what we call local min-max equilibrium, and that is a simultaneous move take on this problem. So we're going to be calling an egg point x star y star a local min-max equilibrium if for some neighborhood delta, no player can unilaterally change their strategy to get an improvement. So the y player, the max player, cannot locally change the y to increase the function, and the min player cannot locally change the function to decrease the function. So these are three possible compromises to this problem that you might be interested in. And again, 1 and 2 are sequential interpretations of this problem. 3 is a simultaneous move interpretation of the problem, but all of these notions are interesting in different sort of like settings. On the existence front, there are differences between the notions. So this notion, number 1, is guaranteed to exist, but of course it's considering global moves for the Y player, and it's going to be too strong to compute, so it's going to be NP hard. The problem with takes 2 and 3 is that they do not actually always exist. So in particular, just to summarize, local min-max equilibrium is a subset of local minimax equilibrium. So this is the simultaneous move version. This is the sequential move version. Both of them are local for both of the players. And both of them are, actually, this inner set, the simultaneous move local equilibrium version, is actually a subset of another interesting solution concept, which is that of fixed points of the gradient descent ascent dynamic, which is this, right? So given a function f, I can consider the projected gradient descent with respect to x, gradient ascent with respect to y dynamic projected on the constraint set. And I might be interested in fixed points of that dynamic. So the comparison between all the notions that I consider is this. And as I said, these two sets might be empty, but as might be clear to you, this red set is actually guaranteed to not be empty. And the reason that this set is guaranteed to not be empty is that it's ultimately a fixed point problem. So this function here, this iteration here, defines a map. And this map, if your function f is smooth, is a continuous map. And by Brauer's fixed point theorem, it has a fixed point. So this set is guaranteed to have at least one solution in it. Okay? So these are sort of like three types of solution concepts that I am interested in this talk.
A quick question, if I may. The main reason we abandoned the global min-max, or let's say the Nash equilibrium, was that it's doesn't always exist, or it's guaranteed to be hard to find. I missed that part.
Yeah, so good question. So as I noted earlier, this problem, so the global min, global max, because S is compact and convex, is actually guaranteed to exist. So global min, global max equilibrium is guaranteed to exist. But of course, that contains within it minimization of non-convex functions. Mm-hmm. And of course, striving for a global optimum is NP hard. It's going to be NP hard. So it contains essentially all optimization. Mm-hmm. Right? So this is the reason we abandoned it. We're trying to look for compromises that are potentially more amenable to first order or lightweight method or in any event polynomial time procedures.
Okay, got it. Thank you.
Make sense?
Yeah.
Yeah. So the first compromise. Yeah. Is there another question?
Yes, there's one more question.
Are you considering the fixed point of GDA or the stable fixed point of GDA?
That is a great question leading up to my next slide. So let me table that question. But is there any other question before I get there?
I think not. I don't see any other question in the chat. Please proceed.
Right. Okay. Good. So as Gauthier I thought it was Gauthier.
Yeah.
Yeah. Okay.
It was me.
All right. So as Gauthier sort of like correctly thought, So what is this discrepancy? What is this discrepancy between these local min-max equilibria, which may not exist, and these fixed points of this GDA that are actually guaranteed to exist? Where is that discrepancy due? And it is reasonable to think that maybe GDA has some unstable fixed points which are not local min-max, and that explains this strict inclusion of fixed points of GDA and local min-max. So, and this is what I would like to discuss a little bit, just to gain intuition about the problem. But as it turns out, stability is not sort of like the reason we see this discrepancy here. So in particular, first thing to notice is that local min-max equilibria may not actually be stable fixed points of GDA. And it's very easy to see that. So if you consider this trivial min-max optimization problem where your function is in fact bilinear, so it is convex concave, as it turns out, the unique solution for this problem is the 0,0 point. But as it turns out, that point is not stable for the GDA dynamics. So first of all, there are local min-max equilibria that are not stable fixed points of GDA. At the same time, there are stable points of GDA that can be a strict superset of local min-max equilibria. And here I'm showing you a very simple example of that, of a function that is concave in Y, but non-convex in X. And what happens in this function is that this point here, the 0,0 point, is stable for GDA, but obviously it's not locally minimax because the X player, of course, at 0,0, the X player has incentive to move to decrease the function since he has a negative coefficient here. But the moment he tries to escape, the Y player has an incentive to correct him, and they're back to 0. So the 0,0 point here is stable for GDA, but it's not a local min-max solution. So another result that you can show.
Sorry to interrupt. Perhaps you could define what a stable fixed point of GDA means.
Yeah, so I have it here. Sorry. Yeah, so it refers to linear stability. Right, so that the map, the Jacobian has eigenvalues bounded by 1. So you'll come back to the point. So one thing you can show is that stable. So okay, so Gautier was both right. So actually right. Okay, so you can show that local min-max are a subset of the stable points of GDA. So that is true, except it holds for strongly local min-max equilibria. So the Hessian must be bounded away from 0 on both sides. Okay, so if that's true, then indeed local min-max are a subset, are stable fixed point of GDA, but this inclusion may fail in cases like this example here where you don't have strict local min-max solutions. So stability is and is not at the root of this discrepancy that we see here. But what I want to argue that this discrepancy is explained by approximation, the discrepancy between these two sets. And in particular, I want to define this following notion of an approximate local min-max equilibrium. So I'm going to be calling a point, a feasible point, an epsilon delta approximate local min-max equilibrium if these constraints holds. So let me parse it. So it's a natural one. I just relaxed the constraint of the local min-max equilibrium by adding a plus epsilon or a minus epsilon on the two sides. So no local move of X can increase the function, can decrease the function. Sorry, I hope I didn't mess up the signs. Yeah, so no local move of X can decrease the function by too much, and no local move of Y can increase the function by too much. So you're almost local min-max. So as it turns out, there is a very interesting, this problem here has a very interesting behavior depending on the relationship of epsilon delta and the ellipticness and the smoothness of the function f that we have. And that behavior is illustrated in this picture. So as delta, so the radius in which we try to find deviation increases from 0 to comparable to the domain size, the problem, the behavior of this problem changes from being trivial to an interesting local regime to a global regime where there's no hope. So I claim that if your delta is bounded by epsilon over the ellipticness, then all points in your feasible set are local epsilon delta local min-max equilibria. On the other hand, if delta is too large, then the deviations that you're considering for improvements are comparable to the domain size, and it's easy to see for reasons similar to the ones that I talked about in my answer to Ioannis. The problem is NP hard, and the interesting stuff are happening in this intermediate regime, where I claim that if delta is bounded by root 2 epsilon over the smoothness, epsilon delta local min-max equilibria are guaranteed to exist, and they're actually equivalent to fixed points of GDA. So I claim that this is an interesting regime to be thinking about approximate local min-max equilibria. Or to say it differently, this is an interpretation of what GDA fixed points are trying to find. So GDA fixed points are trying to find epsilon delta local min-max equilibria in this regime, where delta, the radius in which I'm looking for improvements, is bounded by root 2 epsilon over the smoothness of the function f. So this is sort of like some setup for my problem. And maybe it's another good place to have some questions.
So I don't see questions in the chat, but any questions from the audience regarding, okay, Simon has a question. Go ahead, Simon.
Yeah, so why is it on the right-hand side? Like when you go to delta, which is the size of the constraint set, and thus this is the global view, why do you say you want to have it exist? Because I thought you said they always exist when because of the compactness. So.
Oh, I guess, let me think.
I agree that there are NP hard to compute. So
yeah, I guess.
It's not in a min-max in that sense, because here it's in the sense of Nash equilibrium, but local, while
right.
it was just like globally you just have one side. You just want one of the two inequalities, I think. No.
I see.
Yeah, so Gauthier is right. So this is why I wrote this here. So they exist in a sequential sense, but not in the global sense. And I think I already gave an example where this happens, in fact. And this is maybe here. No, one before. I believe this function already here illustrates what happens. So at any point, at least one of the two players has an incentive to improve, right? So notice that the minimizing player always wants to match y. But if they try to do so, y, of course, wants to escape. So at any point, you see what I'm saying? Like so that's why they may not exist. So at any point, if they're equal, y wants to leave. If they're not equal, x wants to match y. And this is just a very simple reason why they don't exist. So thank you, Gauthier. And this is the thing.
Thanks, great.
Cool. So let me jump now into the main part of the talk, now that we have all the stuff in place. So min-max optimization. So this again is our problem. It's a generalization of the typical min-max problem we're considering. So x and y are constrained together. You want to minimize with respect to x, maximize with respect to y. F is going to be Lipschitz and smooth. My constraint set is going to be convex and compact. And for the next few slides, what I want to do is I want to compare this situation over here with a situation where I have a min-min problem. So basically a minimization problem. So this is just a funny way to write a minimization problem, but just for the purpose of comparison, let me write it this way. And again, the solution concepts I'm interested in are here. So epsilon delta local min-max is the one that the solution concept I talked about just in a couple slides before. Similarly, I can define, of course, a epsilon delta local minimum, which is a one-sided version where, x and y wants to, is looking in the neighborhood of x star, y star, and they cannot decrease by too much. So let's compare these two problems. And let's go to the first level, right, of this game. And the first level of this game is when f is convex. When f is convex and it's lambda smooth, then it's well known that first order methods find epsilon delta local minima for any value of delta in polynomially in 1 over epsilon and lambda and L steps. And the same is actually true for the min-max problem if your function is convex concave. So I hope you all know that, or you suspect that. Indeed, if your function is nice, then first order methods, there's no discrepancy between min-min and min-max. Okay. But of course, the real problem I'm interested in is this, right? So when f is not convex, but it's just Lipschitz and smooth, in that case, it also follows from well-known results that first order methods can find epsilon delta local minima in this local regime that I was talking about before. Delta is bounded by 2 epsilon over the smoothness in steps that are polynomially many in 1 over epsilon, the smoothness, the Lipschitz, and the dimension. So for larger delta, the existence still holds if you go beyond this local regime, but it's NP hard for the reasons that we have talked about a couple times already. On the other side, there's a big question mark of what happens when in the min-max setting if your function is not convex concave. And here's a little vignette of the results that I'm about to talk about. And since I'm giving a talk at Montreal, I decided to use some of my French. So as a Nord-Devre, here's a result for the case where f is not convex concave. So I claim that first order methods need exponentially many steps in at least one of these parameters to find epsilon delta local min-max equilibria in this local regime where they are guaranteed to exist. So even though in the convex and convex concave comparison, min-max was not harder than min-min, the moment you drop convexity on the one side and convex concavity on the other side, while minimization behaves pretty well, at least as far as finding local minima is concerned, min-max is a different ballpark. So the number of steps, the number of oracle queries to function f and its gradient that you need to make to find a local min-max equilibrium is exponential in one of these parameters, in at least one of these parameters, even though equilibria are guaranteed to exist in this regime, as I talked about earlier. So this is a little vignette of sort of like motivating the rest of the talk. This is really a byproduct of the complexity results that I'm about to present. Okay? I
have a question, Costis.
Yeah.
For the theorem in minimization, it's a local minima. It's not a local stationary point. It's not a yeah.
Yeah, it's a local minimum. Yeah.
Because
of course, it holds. So stationary points that may not exist, right? So the function could be a linear function in your constraint set, and stationary points may not exist, right? On the other hand, local minima are guaranteed to exist, and you can find them in these many steps.
Yeah, because I think it's in NPR to detect if like stationary point is a local minima or a saddle point. But I guess it's because of the delta small enough that like you manage to get a local minima.
Correct. And also the guarantee existence this way, because guarantee existence by going to local minima and not asking for stationary points, right? Because as I said just a minute ago, stationary points may not exist, while local minima are guaranteed to exist for any delta, but for this particular delta, also first order methods work.
Okay, thanks.
There was one more question in the chat. I'm not sure that it was addressed by this discussion. So Jack is asking whether we're assuming that the critical points of F are non-degenerate. I'm not entirely sure what type of degeneracy Jack is asking about.
So I'm not assuming, I'm not assuming anything. So take this theorem at face value. So, I guess I can imagine different ways to define degeneracy, but it doesn't matter because take these theorems at face value.
But so I think here, because you're constrained, your local minima are not even critical points, right? Like because the critical points, I guess, are stationary points.
Are not necessarily critical points. They may or may not be. Yeah,
exactly. So I think that's one key difference.
Okay.
Good. So this amuse-bouche was to motivate sort of like the complexity result that I'm about to describe. As I said, this is a byproduct of a complexity theoretic statement. And I would like to introduce you a little bit to the types of tools that you need to develop to be able to get this type of oracle lower bound. And in particular, I want to look at the complexity of min-max optimization in this local regime where the existence of local min-max, approximate local min-max solutions, equilibria is guaranteed to exist. Okay, so again, my problem is F is G ellipsis and lambda smooth now. Set is convex and compact. I'm given access maybe to a projection oracle to that set S. And my goal is to find a feasible point that is I'll tell you what my goal is. So my goal is to give an epsilon and delta in the local regime and a description of or first order oracle access to the function f and its gradient and a projection oracle to S. I want to find an epsilon delta local min-max equilibrium. Another goal that I want to consider is the goal that I stated earlier of finding fixed points of the gradient descent ascent dynamic. So given some alpha and some eta, the step size, and some Akira's parameter alpha, I want to find a fixed point of this mapping. And as I already said, these problems are equivalent. So in particular, So in particular, sorry for my image, in particular to avoid carrying around local regime in max optimization all along. So I'm just going to be looking at GDA fixed points, but I don't know, I might be flipping back and forth between the two because they're equivalent. So again, if F is arbitrary, the above problems seem computationally difficult. I mean, I already told you that about the oracle separation, but I guess so. My goal is to understand what is the nature of these problems from a complexity theoretic standpoint. And of course, the first question you may ask is, okay, these problems are non-trivial. Are they NP hard to solve, this problem and this problem, when the function f is not convex concave? And the answer is no. So they're not NP hard to solve. And the reason is that this problem, which is equivalent to that problem, is a fixed point computation problem. And fixed point computation problems are known to belong to this class PPAD, which is believed to be lower than NP, unless some complexity theoretic collapses that people don't believe in happen. So we are in this weird place, right? So these problems appear non-trivial for non-convex concave functions f. On the other hand, because at least this guy is obviously a fixed point computation problem, they cannot be NP-hard, because fixed point computation problems are below NP. So the situation we're in is this one. So GDA fixed points and local min-max equilibria are somewhere between polynomial time and PPAD, which I'm going to define in a second, but roughly speaking for now is the class that contains problems such as computing Brouwer fixed points or finding Nash equilibria in non-zero-sum games. Okay, so GDA is somewhere here, and the question is it closer to P? Is it as hard as these problems, or is it somewhere in the middle? So in the next few slides, what I want to do is I want to define the class PPAD, which I will later connect to our problems of interest. And I sort of view that, so I feel like there's many beautiful ideas coming into the definition of PPAD and its connection to Brouwer fixed points and Nash equilibria. And I hope I will be able to convey those beautiful ideas. And also I hope that some, at least, of the stuff that I'm about to present will be interesting food for discussions in your dinner conversations in some nice restaurant in Montreal tonight, okay? Assuming they're open. So what is PPAD? It was introduced by Papadimitri in a beautiful paper he wrote in '94. It stands for polynomial parity argument in directed graphs, and it is the class of problems in NP whose solutions are guaranteed to exist, and the reason they are guaranteed to exist is because of this very nice and succinct and obvious and trivial graph theoretic lemma, which says that if a directed graph has an unbalanced node, which is a node with different in and out degree, then it must have another unbalanced node. So this is the handshaking lemma for directed graphs. And it follows trivially from the fact that the sum of in degrees in the directed graph is equal to the sum of out degrees. So if a node is unbalanced, there must be another unbalanced node somewhere in the graph. So now, what does this little trivial statement have to do with fixed points and other things? So the beautiful idea in Christos's '94 paper was that in many proofs in topology and other fields that guarantee the existence of an object, while there is a lot of mathematical disguise around the problem, if you look at the heart of what makes the existence argument, the existence proof work, you will actually discover a trivial combinatorial statement such as this one, or the pigeonhole principle, or some other easy combinatorial lemma. And what Christos discovered is that many problems like Brouwer and Nash, in the heart of the existence proof, hide this actually simple lemma. And what I want to do is I want to convince you why this little lemma lies in the heart of these topological existence theorems. And to do that, I want to introduce to you and prove this very nice lemma called Sperner's lemma. So take an n by n grid, a two-dimensional grid, and triangulate it as shown in this picture, and color the nodes in that simplicity triangulation, using 3 colors, red, yellow, and blue. And you have to respect the colors that you see here in this picture. So in particular, all but this node in the bottom edge must be red, all but this node in this left edge must be yellow, and all the remaining nodes on the boundary must be blue. Otherwise, you are allowed to color the internal nodes in whatever fashion you want. For example, this one. So Sperner's lemma says that no matter how you color these internal nodes, there is always a trichromatic triangle, and in fact, there always must be an odd number of trichromatic triangles. So in the figure you see here, there is exactly 5 trichromatic triangles. There must always be an odd number, and in particular, at least 1. So what I want to do is I want to prove this theorem for you. And what I want you to be observing is that as I'm describing the proof, I want you to take notice in how the parity argument comes up. The other thing I want to note before sort of like and motivating what I'm about to say and why I'm talking about Sperner's lemma here is that you can prove Brouwer's theorem by using Sperner's lemma and some other easy steps. And you can prove Nash equilibrium existence using Brouwer's theorem. So in particular, both Nash equilibrium existence and Brouwer's fixed point theorem can be proven using this nice lemma here. And this motivates the reason why I'm showing you the proof and why the existence of the parity argument in this proof is of importance. So here's what I'm going to do to prove you this theorem. But this thing here is a factory that has triangular rooms, and I'm going to be walking in this factory. And I'm going to declare this bottom left triangle as the start of my walk. So notice that this triangle, all the pillars, every room has 3 pillars, right? So the pillars of this room are all on the boundary. So in particular, no matter how you colored the internal vertices, I know exactly how the pillars of this room are colored. And in particular, I know that this room has 2 red-yellow doors, this one and that one. So this door leads to the outside of the factory. This one transitions to some other room inside the factory. And in particular, I can cross that door to have yellow on my left-hand side. So if I cross that door, I enter into a new triangular room in my factory. Okay? And now your coloring plays a role. If this node is blue, if you colored this node blue, then this room must be trichromatic. Why? Because I entered into this room through a red-yellow door. So if the other pillar is blue, you got your trichromatic triangle, right? Because you entered through a red-yellow door, you found the blue pillar, you're done. The point is that if you didn't color this blue, you colored it either yellow or red, no matter what you did, there's going to be another red-yellow door I can cross having yellow on my left. In this case, you colored this yellow, which opened another red-yellow door for me to cross. And I can keep doing that, right? So I entered into this room, I crossed a red-yellow door, I found a red-yellow door, cross it, and so on and so forth. That will take me to a trichromatic triangle. So now I claim that I sort of prove to you that there is a trichromatic triangle. Why did I sort of prove it? Let me prove it completely. The first thing I want to notice is that I cannot escape the factory. I will never, like if I keep doing this walk, I will never get out of the factory. And there is a simple reason for that. There is no red-yellow door on the factory that I can cross having yellow on my left. There's a unique red-yellow door. And crossing it, you have yellow on your right, not on your left. So if my rule of operation is to cross red-yellow doors having yellow on my left, I certainly not exit this factory because the coloring of the boundary is fixed. You cannot affect it by how you color the internal vertices. So my walk will never leave the factory. The other thing I want to notice is that the only way my walk can stop is if it enters a room through a red-yellow door and it finds a blue. If it does not find a blue, there is certainly another red-yellow door it can cross to keep going. So the only stopping condition is that it finds a blue. So if my walk stops, so my walk cannot get outside. If my walk stops, it must stop in a trichromatic triangle. So the only case that remains is that it's possible that my walk wanders around and then closes a loop and keeps looping around, never stopping. But for my walk to close a loop, it has to create a row shape. It cannot cross the loop into this room, because to cross the loop here, it has to come from the outside and it cannot go outside. So it has to kind of like cross the loop in the middle somewhere. And for that to happen, you have to have a room with 3 red-yellow doors. And that's just impossible. You cannot create a room with 3 red-yellow doors. So I cannot get outside. I cannot close a loop and keep looping around. So I need to stop, because there's a finite number of rooms in this factory. And the only stopping condition is that I find a blue. So there must be a trichromatic triangle. So that's the proof of the first part of Sperner's lemma. Let me prove the second part. So after this first walk that I did settles, I can also do the following mental experiment. Let's imagine that I land into some other room in the factory, for example, that one. If it has a red-yellow door, well, do your business, right? Like follow it, cross it with yellow on your left. That took you to another trichromatic triangle. Now go back here and cross it going backwards, keeping yellow on your left. You got another trichromatic triangle. Do that for any room in this factory. This is what happens. So there are certain triangles that are in paths. There are certain triangles that are in loops. These loops are allowed, right? Because it's not a row shape. It is just a plain loop. And there are some triangles that if you start there, there's nowhere to go because there's no red yellow door here. So abstracting away, and the important thing is that triangles that are endpoints of directed paths go in pairs. So all of these guys go in pairs, except for this main path that only whose endpoint is a valid trichromatic triangle. That's why there is an odd number. But let me abstract away and actually prove the lemma in a more abstract way. So the only thing that I really did, the only intelligent thing that I really did here is to define a transition rule between adjacent triangles. The transition rule was simple. If these 2 triangles share a red-yellow door, cross it, having yellow on your left. By the mere definition of this transition rule, in effect, what I did is I defined a graph. The nodes of this graph are the triangles of my factory. Every triangle has at most one triangle that it can go to going forward, and at most one triangle it can go to going backwards, because you can only have at most one red-yellow door that you can cross going out of this triangle having yellow on your left, and at most one you can cross going backwards with yellow on your left. So the directed graph that I defined has in degree and out degree at most 1. So graphs that have in degree and out degree at most 1 are very simple. They are directed cycles, directed paths, and isolated vertices. And here's the thing. My graph has at least one vertex, namely the bottom left triangle that touches my boundary, the starting point of my walk, that is an endpoint of a path. So what happened here? On the other hand, all other endpoints must be trichromatic, because the only nodes that have in degree 1 and out degree 0, or in degree 0 and out degree 1, they must be trichromatic. So effectively, all my vertices belong in one of these categories. All the degree 1 vertices are trichromatic, except for this boring one that I started from. All degree 2 vertices, they have no blue. They cannot have a blue vertex, because degree 2 vertices must have 2 red-yellow doors, so they cannot have a blue. And the degree 0 vertices are all other triangles. And the fact that there is always a starting point, there is at least one path in this graph, establishes the existence of at least one trichromatic triangle. The fact that endpoints of paths go in pairs establishes that there is an odd number of trichromatic triangles, because all endpoints are valid except for the boring one. So this is really what took place in my Sperner lemma. And hopefully the definition of this class PPAD makes sense now. So PPAD contains all problems in NP, which, like the Brouwer problem, ask you to find unbalanced vertices in a huge but implicitly defined undirected graph. Okay? Such problems define implicitly some directed graph. They give you a boring unbalanced vertex, and they ask you to find another unbalanced vertex, which is guaranteed to exist because of the parity argument. Okay? So if I were to take questions now, here's an obvious complaint, right? That, look, we did graph algorithms in the first class in algorithms, and these types of problems are boring because, okay, I can inspect all the vertices in a graph, and I can look at their degrees and find, which nodes are unbalanced. Okay, so this sounds like a boring type of problem. But here's what I want you to have in mind. The types of problems that are actually interesting in this space are problems that, like the following. So consider a Sperner problem where the colors of the vertices are not given explicitly to you, but you can query a circuit that will give you the color of a particular vertex. So in particular, you imagine a huge exponentially sized grid, and you're given a circuit that takes the coordinates of a point, which are n-bit strings, and gives you the coloring of that vertex. And the challenge is, given the circuit, you want to identify a trichromatic triangle. Of course, you could follow my proof and do sort of like a lazy evaluation of the circuit until you hit a trichromatic triangle. You are guaranteed to hit a trichromatic triangle if you follow the proof that I used to prove Sperner's lemma. But the problem is that in an exponentially large grid, it could be that this walk takes exponential time to settle. And this is the difficulty of the problems in PPAD. The problems in PPAD, they give you a directed graph that is huge and it's implicitly defined. And they ask you to find unbalanced vertices in those graphs. And this is really why the class is hard. And as far as we know, is somewhere between P and NP, but different than P. So this class contains very interesting problems, as I alluded to before. It contains Brouwer and Sperner. We also showed, Ioannis talked about that. We also showed in 2006 that Nash equilibrium is also a complete problem for that class. And in particular, what this says is that these problems are both solvable by the directed parity argument in huge graphs, and they are at least as hard as any other problem in this class. And this is really the type of result that complexity theory tries to obtain, right? So complexity theory is striving to define complexity classes that capture exactly the complexity of problems of interest. And in this scenario, the class PPAD that Papadimitriou defined in '94 was successful. It captured all these very interesting problems exactly in the sense of completeness results. So back with this little detour, back to our main question. What we showed in this recent work that I'm presenting today is that finding fixed points of gradient descent ascent is PPAD complete. So in particular, it is exactly as hard as finding general Brouwer fixed point, not fixed points of only this particular function, but of any function. exactly as hard as finding Nash equilibria in general sum games, even though here we're talking about a zero-sum game, and any problem in PPAD. And the same is true for approximate local min-max equilibrium in the local regime because they're equivalent to this problem. So a byproduct of this proof here that we did to show that this problem is PPAD complete is an oracle lower bound, the oracle lower bound that I mentioned earlier, that given oracle access to a Lipschitz and smooth function f and its gradient, finding approximate fixed points of the GDA iteration requires exponentially many queries to the function or its gradient, which are exponential in 1 over alpha, the Lipschitzness, the smoothness, or the dimension. And the same is true for finding local min-max equilibria in the local regime. So, so with this sort of like brief detour on complexity theory, the complexity theory of fixed points and Nash equilibrium in particular, I hope that our complexity theoretic results now make sense. And this oracle lower bound, which are have nothing to do with complexity theory, they're just query, like in the standard oracle model, are byproducts of the constructions, the types of constructions that we have to do to prove our main result. Are there any questions about this segment of the talk?
Any questions? I don't see any questions in the chat. I think, but maybe Gautier has a question. He's unmuted.
Okay, but Simon has questions too. But let me ask mine.
Oh,
I have two questions.
I missed them in the. I missed Simon's message in the chat. Please go ahead, Gautier, and then we'll ask Simon.
The first question is like, so you're always considering S compact, so bounded. Do you think it's just for like the sake of the proof? Is it really important or not? Because like, for instance, in practice, usually S is like, I mean, there is no constraints usually. And in like minimization, usually like non-convex minimization, we deal with like the unconstrained problem too.
Yeah, so I'm not a huge fan of the unconstrained setting. And
Okay.
I'll tell you why. So first of all, like the moment your set is not bounded, equilibrium existence is gone, right? Because you can have this linear function that goes to infinity. So it's not meaningful to be talking about local minima, global minima, local min-max equilibria, fixed points of GDA, whatever. It doesn't make sense.
So
typically in the unconstrained setting, what people do to get existence is they put upper and lower bounds on the function, right? So they assume that the function, even though it's unconstrained, is uniformly bounded. And typically, these types of assumptions make the problem easier, in a sense. We have not considered, so for local minima, of course, we understand what's going on in terms of both existence and computation if you're unbounded, but you're lower bounded. In the non-convex, non-concave case with bounded functions and unconstrained setting, I don't think we have thought a lot about existence or computation. But yeah, my sense is that you're not going to be getting positive results there. The only thing maybe you could, the only thing you might be doing is getting NP hardness instead. So I don't think that yeah, the unconstrained setting is gonna help in some way.
Can I ask something on exactly that point? Interjecting a little. So the reason you said that it cannot be NP hard is because we're guaranteed that it's guaranteed to exist in the compact case, right? So the decision problem is always yes. So it's meaningless to talk, but you could ask something about its position or something like that that could be NP hard, right?
Correct. Yeah. I mean, there are many known such results also for like Nash equilibria. For example, if I ask you, are there 2 solutions versus just one? So you're guaranteed to have one. Like if you ask the questions, are there 2 of them? That's NP hard. If you ask, okay, I know there might be many, but I want the one that maximizes something else. That's NP hard.
Any property is this first coordinate between 5 and 10 or something?
Right. Yeah. All of these are going to be NP hard.
I see. And but now I guess what we're saying is that in the unconstrained case, even the existence of GDA fixed points could be NP hard.
As far as I can see, yeah.
Okay.
Yeah. I mean, maybe I already gave an example, right? Like, I mean, okay, unless the function is bounded, but still, I don't think you can escape this type of like x minus y squared type of result, right? So I'm imagining you can create a situation where one player is chasing the other, and because there's an infinite domain, they can always chase each other. Okay, so you can have kind of like, I don't know, a sinusoid or whatever. I don't know. Like I have to think about it a bit carefully, but I feel like you can keep your function bounded, but you can have the 2 players chasing each other to infinity.
All right, we're going to be running out of time soon, so maybe we can get a quick question from Simon, because he had a question, and then we should
wrapping up. Yeah.
With a conclusion.
Okay, so I had many questions, so I'll have to pick one. Amazing talk, by the way, super interesting.
Thank you.
So I guess the question I ask is, and then I can ask you other question just to you later. But what about the extra gradient in terms of dynamics versus this GDA fixed point? Like, does it bring anything here, or what's the terms?
Good question. I have not thought about it. You're asking, basically you're asking, I mean, okay, of course, local min-max equilibria is a notion that can be defined in the absence of a particular method, like as not like this stands on its own right. Now your question is, if I wanted to find fixed points of extra gradient, could that become easier or harder or whatever, right? So the obvious answer is it cannot become harder because it's still a fixed point thing. So it's going to be in PPAD. And I believe that it's going to also be PPAD complete. So I don't think you will get any. Yeah, so you're not going to get, and like, I mean, I'm pretty sure you can build the connection between fixed points of extra gradient and the notion of approximate local min-max equilibria that I talked about, and because these are PPD complete, the other ones are as well. Yeah, so that, yeah, I don't. Another question you can ask is, what if I define fixed points of GDA like a second-order method type of thing? And I think again you will get the same types of results. So I don't think, so I don't think that changing the method whose fixed points you're looking at is gonna change the picture.
Okay, so I think let's move on, and if we have time in the end, we might have a few more questions.
Yeah, so I'm at the exaction point here. There's no way I can present a proof because it's a super long proof, but here is like a very non-honest description of the proof. So to prove that the problem is PPD complete, either GDA fixed points or local approximate min-max equilibria, you have to take a problem that is already known to be PPD complete. For example, the problem Sperner that I showed you earlier, and you have to reduce that problem to finding fixed points of GDA or local min-max equilibria. And this is what we kind of do in this paper, okay? So very, very roughly speaking, and again, I'm not being super honest here with the complexity of the problem at hand. We take an arbitrary instance of Sperner, and we create a game between two players, an edge player and a triangle player. So the triangle player chooses a triangle in this picture, And the edge player has to choose an edge in that triangle. And the function value, how much the min player plays the max player, is decided by, it has to be locally computable, because this is the notion of reduction that will give you this exponential type of lower bounds or PPD completeness results. It has to be like this reduction from Sperner to the game that I'm describing has to be locally computable from local information. And the value depends on whether the triangle player chose a triangle that has at least one red-yellow edge. And it also decided by whether Y chose a red-yellow edge and whether the orientation of that red-yellow edge in the triangle is the right one. And sort of like the way we want to define this game is so that the best response dynamics follow these potentially super long, exponentially long paths in the triangle, in the Sperner instance. Roughly speaking, here's a simulation of what is happening. So if the triangle player, who is the max player, chooses this triangle, and the edge player, who is the min player, chooses this edge, the function value is +1, which creates an incentive for the edge player to choose the other edge, where the function value is -1, which creates an incentive for the triangle player to choose the other triangle to make the value +1, and so on and so forth, trying to simulate these long paths in this Sperner instance that require a lot of queries to the circuit to be understood, to be identified. Now, the other remark that I want to make is, why the heck can I not do this if I had a min-min problem? Where is the min-max? Why is min-max different in nature than min-min? And here's an approach to do a min-min implementation of this idea. So the min-min implementation says, okay, look, like the triangle player chose here, the other player chose there, let's make the function value +1. And then give the incentive to the triangle player, to the edge player to move here to improve the function value, to make it even smaller. And also then give an incentive to the triangle player to change triangles to make the value even smaller. And then change the edge to make it even smaller, and then the triangle to make it even, and so on and so forth, right? So you could, in principle, try to do this kind of thing. But what's important to note here is that for this type of implementation, you need memory. You need to know where in this super long, exponentially long path you are located to be decreasing the function value like that. The cool thing about min-max is that flipping from 1 to -1 to 1 to -1 in the best is, along this path allows you to have best response dynamics with no memory that are locally computable based on the local colors in the triangle. So from the perspective of trying to build either a complexity theoretic reduction or a oracle lower bound, the function value must be computable locally. It shouldn't be telescoping exponentially long paths to be computed. And this is the inherent reason why in our reduction, we need to use the power of min-max. And this is what distinguishes min-max from min-min. Okay? Now, a lot of details have been omitted from this discussion. I have to decide what happens if the triangle player chooses triangles that are outside of this Sperner paths. What happens if they're on the boundary? And a super important technical problem that we faced is, after you define this 1 - 1 best response type of dynamics and the function value there, how the heck do you make the function ellipsis continuous and smooth in the whole domain? That was a huge technical issue, but especially in high dimensions. But I hope I sort of gave intuition about why min-max is different than min-min, and how you start with this exponentially long paths in the Sperner instance to construct a function whose min-max equilibria are very hard to locate by querying the function at different points in this square. This was sort of like the summary of what I wanted to say. Just to summarize, we showed that computing local min-max equilibria in this local regime is PPAD complete. The same is true for fixed point of GDA. I want to emphasize that what this theorem says is that any algorithm, not just first order, second order, or whatever other algorithm you want to construct, no algorithm is going to work, is going to take, any algorithm will take super polynomial time to find local min-max equilibria. Unless, of course, PPAD collapses to polynomial time, which we don't expect, right? So one way to view this complex theoretic result is as a lower bound saying that no algorithm, first order or not, will actually be able to compute these points. But sort of like if you exploit the structure that a proof has, you can also get an unconditional result that says, regardless of whether P is equal to PPAD or not, first order methods must make exponentially many oracle queries in at least one of the problem parameters to find a local min-max equilibrium. And sort of like in ongoing work, we're saying, look, forget about polynomial time algorithms. Let's at least get some procedure that converges to these local min-max solutions. And again, exploiting the understanding that we got from this complexity theoretic result and lower bounds, we are able to come up with a second order method that asymptotically converges to local min-max solutions, and in particular avoids this cycling issue that we know exists in min-max optimization. So to conclude, min-max optimization and equilibrium computation are intimately related to the foundations of game theory, mathematical programming, and online learning theory, with profound applications in statistics, complexity theory, and other fields. But I think they have already found and will find a lot of interesting applications in ML. And machine learning poses some interesting challenges that have to do with the high dimensionality of the problems and the non-convexity, concavity of the objectives. I think these applications will explode as ML turns more to multi-agent learning applications and situations where your system is so complex that you introduce other agents to enforce constraints on your learning system. So what I showed today is intractability results, both complexity theoretic and unconditional oracle lower bounds, for finding first order local min-max solutions or fixed points of GDA. And the main open questions that are of interest to me right now are A, I said that earlier, asymptotically convergent methods. B, to consider cases with special structure, and one particularly interesting one that we are considering in joint work with Noah Golovitz and Dylan Foster is that two-player is the class of two-player zero-sum reinforcement learning settings, where you have this interesting situation where the min-max theorem holds, as shown by Shapley, yet the objective function you're dealing with is not convex concave. Finally, I'm super interested in multi-agent equilibrium computation and learning settings where the landscape is very fertile for uncoupled learning methods. Before I thank you, I would like to say that the results, the hardness results and the oracle lower bounds have been obtained by joint work with Stratis Koulakis, who's a postdoc at SUTD in Singapore, and Manolis Zampetakis, who's always is, but my PhD student who just graduated, just defended on Monday. And As I already stated in the talk, but I would like to emphasize that this is due to the great work of these two students. Thank you very much.
All right, thank you, Kosti.